It's fine. Okay, great. So let's get started with today's lecture. So I first wrote a very simple kind of course objective. So this course, the first lecture has 3 objectives. So the first is to allow you to understand machine learning from kind of a zero background. So I do assume you have some background in Python programming because we will be talking about actual codes in this lecture. The second is to solve a nuclear physics problem using real detector data. So not some simulated handwritten digits or anything like that. So we actually have some open data set, time series data set from the Marijuana demonstrator experiment that both Walter and I are working on. So the third is going to be providing you kind of like a building block for more advanced model that we will discuss in tomorrow's lecture, and also some of the possible generalization to other experiments. So this lecture will be here is kind of the outline of my lecture. So on the top is how we are going to flow through this content. So we start from how we are actually processing our data. So we don't start from the machine learning model, but we start from the data. So how we can actually pre-process, organize our data into a format that we can use to train a machine learning model. And then we will go to the feature extractor. So the model building part, which is the most important part of machine learning. So this is going to be split into a feature extraction part of the neural network, plus 2 possible tasks we can do, including classification and regression. And then we will talk about how we can train a machine learning model, and lastly, how we can evaluate the performance of our machine learning model. So throughout this lecture, I will use 3 kind of blocks to kind of outline different kind of content. So the first one is a dark blue block is a theory. So it's going to contain important kind of equations or theoretical derivations that you should understand to understand the mechanism behind machine learning. So the second is this magenta color block is called concept. So it's some of the fundamental concepts that I'm going to mention that kind of show up in all the different places in the machine learning world. And lastly, I will have this yellow block, which is code. So we will actually have some code on the screen, and I will explain to you how those code actually works. So this is the actual implementation side, and it will be very useful for building your own models. So at the end, I'm going to provide you a Jupyter notebook, which contains all the code I have shown you. And you can use that Jupyter notebook to actually analyze this Marijuana demonstrator data that I mentioned earlier. And more importantly, you can modify this code to do analysis tasks on your own experiment. So this is kind of the way I'm designing this lecture. So let's start with this lecture with actually some kind of physics, just 2 slides of physics, then we will jump to the machine learning side. So this is the first section, which is data pre-processing. So I want to start by talking about the detector we are actually using and what kind of data it actually produces. So first, I want to talk a little bit about light-emitting diode, or what we call the p-n junction. So this is a semiconductor device where you put a p-type semiconductor and n-type semiconductor together. So when you put this together, you will have some electrons and some holes, and they will recombine in this region. So after they recombine, this region will be void of charge. So this region is what we call a depletion region. So basically, the light emitting diode that you have seen every day. So for example, your cell phone screen is made of this kind of device, is actually made of this kind of p-n junction structure. So the detector we are going to use in this lecture is called a high purity germanium detector. So the idea of high purity germanium detector is that when you have a p-n junction, in order to create the depletion region, you need to create a voltage across it, apply voltage across it using a battery like this. So, but when you are building a high purity germanium detector, what you are doing is that you are flipping the order of your battery. So here you have positive on the left, negative on the right. Here you have positive on the right, negative on the left. So if you have a p-n junction and you reverse the direction of your battery, what you can do is that you can increase the size of this depletion region where there is no charge. So if you have a higher voltage, you can increase it even further to cover the entire body of your semiconductor device. So this semiconductor with a full depletion region become a very nice detector that we can use. So the only thing about this kind of device is that it's very hard to build it large. So each of the detector we can build using this reverse depletion technique is only about the size of my palm, so it's very small. Because of this, if we want to actually build a larger detector, what we need to do is to build an array of these very small detectors. So this is basically what we are using in the Majorana demonstrator is a high purity germanium detector array to search for neutrino-less double beta decay, which you have already heard from last week's lecture. So when a neutrino-less double beta decay event happens in your high purity germanium detector, it's going to deposit all of its energy in a very localized point-like location. So this is going to create a lot of charge in this region, and remember, we apply an electric field over our semiconductor detector. So this charge are going to drift to this little point contact on the bottom of our detector. And if you read out the voltage at this point contact, you will see this very nice waveform, as you can see on this right plot. So most of the background events in our detector, in our high purity germanium detector, are going to be photons that scatter multiple times in your detectors. So this means it's going to deposit its energy at multiple different locations. So here you can see, but if this happens, then what you will see is you have two different charge clusters that drift to this point contact on the bottom. And if you read out this voltage, you will see this kind of multi-step-like waveform, which is in contrast to the single-step-like waveform you have on the top. So this actually looks pretty different. So on the top, our signal event is what we call the single-side waveform, which is like a single step. And our background event is this multi-step-like waveform, which is what we call the multi-site waveforms. So just looking at this waveform, we can actually extract a lot of useful information by doing some post-processing. So for example, we can take a derivative of our waveform and convert it into the current space. And then we can see how tall this peak is in the current space. So we can see if we have a single site waveform, which is our signal, the peak is going to be taller. If you have a multi-site event which has multiple energy depositions, the height of this peak is the current peak is going to be smaller. So this is what we call the amplitude versus energy, or A versus E parameter that we can build by processing this waveform. So this is one of the physics parameters you can extract. So some of the other parameters, if you just read out how tall your waveform is, that is corresponding to the energy of this events in our germanium detector. And if you calculate the slope of the tail of your waveform, so that is another parameter we call tail slope. That is very useful for rejecting surface background, what we call the surface background. And lastly, you can read out how long this charge drift from the creation point to its point contact from this like blue region. And this is what we call the drift time. So it kind of tells you the location of where the event happens in your germanium detector. So there are a lot of other information you can kind of read out from your germanium detector. I do want to mention that we have in the Majorana demonstrator experiment, we have released our data, part of our calibration data to facilitate the community to do a machine learning analysis. So this data set is actually on the Zenodo, is purely open, and we also have a document that describes our data set. So this is the real data from one of the state-of-the-art physics experiments, and feel free to play with it to do your own machine learning project. So this data set, so one file of this data set would contain 65,000 waveforms, 65,000 data points. And for each data point, it contains this information that's listed in this table. So first, it contains a raw waveform produced by the high purity germanium detector. So you can see these are actually what we call the time series data, which is like a one-dimensional array where each time index corresponds to the voltage reading, as I told you on the last slide. And you can see here are some of the raw waveforms that I pulled out from this data set. And it also contains some what we call the ground truth information, like what those waveforms actually are. So for each waveform, it contains an energy label, which tells you what is exactly the energy that we derive from our traditional analysis. And it also has some other, so remember this energy label corresponds to the energy parameter I told you how to extract on the last slide. And we also have some other PSD labels, which correspond to what kind of event this event are. Is it a signal, or is it a background, or is it this type of background? Is it some other type of background? So those are basically, so for energy, you have a flow point number. So it can be anything. It can be 3 MeV, 5 MeV, 0.2 MeV, anything. But for the PSD label, it's basically a binary. It's either 0 or 1. So if it's 0, it means this event is a background. If it's 1, it means this event is a signal. So so for each waveform, we also release all of these very useful analysis labels for you to kind of train your machine learning model. So all of our data, will be stored in this HDF5 format. And basically here I pull out one of the file called mgdtest2.hdf5, and you can see what kind of information is stored there. So we have the raw waveform, which contains 65,000 data points, as I said, and each waveform's length is 3,800. So it's a 3,800 array, and each array contains a value, right? The value is basically the ADC readout of our detector. And we also have this label. So each of the label is an array size of 65,000. So for the PSD label, it's just 1 or 0. For the energy label, it's a flow point number, which actually tells you what the energy of the waveform is. So here we will talk about we'll very briefly talk about how we can read out this information using code in Python. So we can actually use this so-called H5PY package, which is very commonly used. So if we open up this file using this H5PY file command, we have this file, and then we can simply just index the file. For example, if I want to read out the energy, I just index it with energy label, and then I can read the energy. And if I want to read out the actual waveform, what I can do is that I can just read out the waveform field by doing file raw bracket raw waveform. So it's very easy to access HDF5 file after you load it using this package. So now let's take a look at all the raw waveforms we get. So remember, those are all real data from the Marijuana demonstrator experiments. So we can look at, so here I plotted some of the waveforms. So you can see they all look like this. And I have a title for them. So some of them are background noise that we want to reject, and some of them are neutrino signal that we want to keep for our experiments. And well, just by looking at this, I actually saw some problem about it. So what's the problem? So first, my waveform has such a long tail, right? You can see, if you look at the waveform, most of its region is tail. But the tail is actually not very interesting because the tail is purely an effect of my DAQ readouts electronic effect. All the physics, well, at least most of the physics is happening within this rising edge of the waveform. So this is the most interesting part we want to study. But if I look at the raw data, I only see the tail for most of the part. So the second alarm is, does my waveform all start rising from the same location? You know, maybe I have some of the waveforms that start writing at 500, some of the waveforms start writing at 2000, some of the waveforms start writing at 1500 or whatever. So that's another question.
Yeah, sorry. Just to clarify, the PSD label low, ABSC.
Yeah.
So equal to 1 just means neutrino signal. Equal to 0 just means.
Exactly. Yes. Yes. Exactly. Yeah.
So how do you define your signal and background here?
Oh, the signal and background is actually, remember, our data actually come with this analysis label. So are you asking how this label are obtained?
Yeah.
So this label are actually obtained by our analysis, which was done by our analysis team over the past 5 years or so.
So your signal means the signal you have like in your region of interest, and background is. No,
this is a cut that we apply to every single waveform.
So it's good enough cut, something like that.
Yeah, we spend a lot of time tuning this cut, so that is and we did a lot of calibration and validation on our calibration data set to make sure it's correct, it's physically correct.
But there's signal like across all energy. With energy covers
At least most of the energy, I guess, not all energy, not very low energy, but at least for most of the energy, yes, yeah.
What's the time scale we're looking at?
So the time scale, I think I have it on this plot. Yeah, so sorry, it's gonna take. Yes, so you can see this is in microsecond. So you can see we are going from 0 to like 30 microsecond or so. Yes.
Okay, thank you.
Yeah.
It's 10 nanoseconds per time.
Okay, any other questions before I go forward? Okay, great. So yes. So the second alarm is that waveform may start rising from the same from different position. So that may cause some problem to our model. So luckily, it's not a problem in this data set because before I released this data set, I actually matched all the waveforms to start writing from the same location. But in real experiment, like if you are working on your own data, maybe you need to think about this kind of thing. Are your waveform all start writing from the same time indices? And if not, would that have an effect on your machine learning model? And lastly, your waveform have different heights due to energies, because I told you a higher energy waveform will be rising higher. So here you can see some of the waveform are very low and some of the waveform are very high. They even go out of the scale of my plot. So all of this alarms is something that we need to address before we can actually build a machine learning model. And the way we can address it is through data pre-processing. So the concept of data pre-processing is to transform our data in certain ways so that the unwanted features that I'm worried about that's going to affect my machine learning model got kind of filtered out by doing this kind of thing. So this is even before you start building your model, right? This is the thing you need to think about before you start building your model. So the first kind of data pre-processing that we can use is windowing, basically. So instead of looking at the full data set, which contains like 38 microsecond of waveform information, we can only look at a specific part of this data set. Like for example, if we look at this waveform, so before I have this full 3,800 samples, but most of them is tail, which I'm not very interested in. So what I can do is I'm only selecting waveform between 500 and 1500 that contains the rising edge. So after I do that, you can see this waveform is this waveform becomes something like this. So it's a very simple data pre-processing. Actually, this event is a background noise. If you look at this full version, it's very hard to tell why there are two kind of rises, right? But after you do the windowing, you can see here there is a little kink, which is a hint of why this event is a background. So the second kind of processing is normalizing. So so the idea is to make sure that all the waveforms are of the same height. To remove is energy dependency. Because when we are building a machine learning model, we wanted to perform, say, classification, background rejection across all the different energies. So the code to do this is actually very easy. So we can just say our waveform normalized is equal to waveform minus waveform domain. Minus is smallest value divided by waveform max minus waveform domain. So that's the maximum possible value that it can take. So after that, so you can see before my waveform can go to any values. So this waveform rises all the way to 5,000. But after you normalize it, you can see a waveform just varies between 0 and 1. And you can do this for every single waveform. So if you do that, you remove the energy dependency, which is something you don't want when you are training your machine learning model. So the last kind of data pre-processing technique I will talk about is called standard scalar. So this is like a more common kind of data pre-processing technique that is used in many different machine learning models. So the idea of standard scalar is to transform each dimension of your data so that it has mean equal to 0 and standard deviation equal to 1. So here, after windowing my waveform, my time series data has 1,000 sample, right? From the first time, second time, all the way to the 1,000 time. So it's a 1,000 dimensional data set. And if I do standard scalar, what I'm doing is I'm transforming each of the dimension, each sample of my time series, each sample of my waveform into a case where its mean is 0 and standard deviation is 1. So you can see here on the top, I have the unscaled waveform on top. And on the bottom, I have the waveform after standard scaling. So you can see here, at the beginning, most of my waveform is like at 0. And after transferring is, some of the waveform is at minus 0.5, some is at 2. But the mean, if you pull out this sample at 0, it's going to be 0. And if you calculate the standard deviation of this full waveform at time 0, it's going to be 1. The same for this rising part. So where if you pull out this, let's say 500 time index, and you calculate the mean is going to be 0 and the standard deviation is going to be 1. So you can see it kind of distorted waveform into this kind of format. So this is a very useful way to transform your data for machine learning, for various kind of machine learning models. Then I will talk about how we can do, how we can put everything together into a PyTorch dataset class. So PyTorch contains this class called datasets that we can use to build our data loader. So it contains these different functions. We will talk about each of them. So the first function is the init function, which is pretty standard in Python. So it only called once when you are initializing a dataset object. And so basically what you should do here is you should read information from your HDFI file into an array. And you can apply dataset level pre-processing like standard scalar, because when you are doing standard scalar, you are normalizing each of your index from your entire dataset to have a 0 mean and one standard deviation. So here, for example, if I read my dataset, I'm going to have this arrays. Self.waveform has a size of 65,000, 1,000 after the windowing processing, as I said. I can read out the energy, right? So the energy contains 65,000 flow point number, each correspond to one of the waveform. And I can read out the PSD label low A over C. That's the one we are going to look at today. So that's also contains 65,000 values of either 0 or 1. If it's 1 is a signal, if it's 0 is a background. So the second function is this underscore len function, which returns the length of your data set. So it's going to be called whenever you run this len over your data set objects that you define. And in this case, the way we should write it is just return the value of 65,000, right? Because we have 65,000 waveform in total. So my len function should just return 65,000. So the next function is probably the most important one, which is called get item. So this get item function is going to return one data point as a given input argument indices. So IDX is the input location of where I want to return one data point. So this, so for this, we can apply some kind of data point level pre-processing. For example, if I want to normalize my waveform to all have a height of 1, I can put the processing here. So basically, this function should return self.waveform. Remember, we define self-waveform here, which contains all of our data. So I return the waveform at IDX location, right? So I put IDX, I index IDX of my array, and also self.PSD label IDX, self.energy label IDX. So this is how I'm returning it. But I don't want to give you a warning because this function will be called very frequently when you are processing your data. So basically, you don't want to put something that's very slow here because otherwise the entire process is going to be very slow. And besides that, you can define any kind of helper function, as many helper functions as you like when you are building this data set object. So after having this neutrino data set class defined, we can actually build what we call the data loader that we're going to use to train a machine learning model. So we start by defining the data set object by calling the neutrino data set. And then we need to obtain training and validation indices. So indices is just an integer that tells you which location you should be calling your data set. And then you want to shuffle all your indices. So you start by, and then you want to define a sampler class that is also provided by the PyTorch kind of environment. So you don't need to worry about it yourself, but you can just create a sampler from this indices list. And lastly, you can create a data loader, as you can see, by combining your data set object and the sampler using the bottom lines of code. So after that, we will have two loader. One is called the train loader. That is what we are going to be used to train my machine learning model. And the second is called the test loader. So the train loader contains 70% of the data, and the test loader contains 30% of the rest of the data. So they are mutually exclusive. They are different part of the data. So we will train our model using the train loader, and we will test its performance using the test loader. So this is all we need to get out from our data pre-processing part. And then, so there's one more context, which is the batch. So the ideal batch is that we can group n waveform into a 2D array. So remember, each of our waveform has a length of 1,000. So, but if we have a batch size of 25, then we have an array of 25 1,000. So we're grouping 25 waveform together into one 2D array. So you will see why we can do this in the future slides. Okay, so now we finish pre-processing our data. We want to go to question.
So you chose a ratio of 70% of your data for pre-processing. Why 70%?
Well, I choose the ratio of 70% as my training and the 30% as my validation.
Just splitting. So why 70%?
Well, it's kind of random. So you can choose any number you want, but you generally want to choose use more training data than your validation data, basically, because it's better to train with a larger data set in general. Okay. Yes. So after the data pre-processing, we will actually start talking about how we can build our model. But what kind of model do we want to build? So we have our input time series data waveform from Marana, which is an array of size 1,000, batch size 1,000, basically. And my model should be mapping this batch size 1,000 array into some kind of output, right? For example, if I want to do signal versus background classification, then I want to output something like batch size 1. And this 1 is kind of my classification score. And this score should be kind of reproducing our label to the best of its capability, right? Remember, our PSD label is just a value of either 1 or 0. So I want my score to be as close to my PSD label as possible, basically. If I want to build a energy filter, let's say for my time series data, then I need to build a model where my input is batch size 1000, it's the same data. And the model should output something of batch size 1, right? So the one value I wanted to best reproduce my energy label. So what energy each of the waveform is. So this is kind of the overall flow we want to do for our machine learning model. So now the question comes, how do we actually build this model? Like what kind of component is needed in this model? So for this, we will actually go into this part, which is called the feature extraction, and we will talk about what it is. So we will start from this so-called perceptron model that was first invented in about 1970s. So this model is actually very simple. So remember, you have a time series of size 1000, is an array of size 1000. And so basically your input is going to be x1, x2, x all the way to x1000. So a perceptron basically just assign a weight to every single element of your waveform. So it has a W1 correspond to x1, it has W2 correspond to x2, and all the way to W1000 correspond to x1000. So, and you also have additional weight W0, which you got multiply to 1. So this is kind of like the bias, is the bias of your model. It's a fixed weight you add to all your data. So what you do is that you multiply each weight, so the weight to each of these inputs, and you sum them up together, and you feed them into a step function. So a step function is very easy. If there a board, I can draw anything. Maybe if not, it's totally okay. Yeah. Oh yeah, that's fine. That's good enough. Yeah.
Yeah.
So a step function is very simple, right? So it basically gives you a 0. So this is your x input, this is your y. So if your input is smaller than 0, it gives you a 0. If your input is larger than 0, it gives you a 1. So it's a very simple function. How do I lower it? Sorry about that, Walter. Yeah.
And if you want to use the board a lot, you can switch over to.
Oh, yeah, no, I'm only gonna use it once like this. So that's it. Yeah. So yeah. Yeah. So this perceptron learning model is when it was first invented is to some extent boring because it's what we call the linear classifier. That means if you have two clusters of data points, you can only draw a straight line between these two clusters. So people are not very excited about it. What makes it exciting is this modification. So we are kind of we are kind of converting a perceptron into what we call the neuron. And the idea of converting perceptron of neuron is just by replacing this this step function into what we call the nonlinear activation function. So this nonlinear activation function can be anything as long as it's not a linear function. So it can be a hyperbolic tangent, it can be polynomial, it can be anything. So by converting this step function activation into this nonlinear activation function, we actually turn a perceptron learning, we actually turn a linear classifier into a nonlinear classifier. So that means between two clusters of data points, it can not only draw a straight line, but it can also draw a curved line. So this makes this model become much more powerful. So in this, remember, for a single neuron is only looking at this input waveform using its own set of weights. But we don't have to have only a single neuron, right? We can have many different neurons. We can have 1,000 neurons, 10,000 neurons that's all looking at the same waveform, and each neuron is going to carry their own kind of set of weights. So basically, this will make what we call a layer of our neural network, which basically contains many parallel neurons that are all looking at the same kind of input of my waveform. So because of this, when we are defining a neural network layers, we need to define this kind of the following kind of information. First is how many input do I want to feed into my neural network layers? So in this case, since my waveform only has 1,000 input, right? So my input dimension for the first layer should always be 1,000. And the second is how many outputs do I want to have for my neural network layers? So this is something that you can define yourself. You can let it output 500, 300, 200, or 1,000, whatever you like. And lastly, you need to define what kind of nonlinear activation function you want to put into your neural network layers. So the lastly, the idea is you can have one layer that's looking at the waveform. But you can also have more layers that's above this first layer, right? So what we call the deep neural network or deep learning, the idea is to have a very, very deep neural network that contains many of these layers. So you can see here it has 1, 2, 3, 4, 5. It's a 5-layer neural network. So basically, this is what it means by deep learning. Okay, so now let's try to build our model to output these quantities I want. So remember my input has a size of 1000. And I wanted to output, let's say in the signal versus background classification situation, I wanted to output something with a size of 1, basically. So in this case, what I should do is that I first should build a layer of 1000 input and 512 output. So this number is kind of arbitrarily chosen. I just choose my favorite number pretty much. And then I feed it into activation function, which is also something I choose. And then my second layer, remember I have deep neural network, so I can have multiple layers. So my second layer takes the input of 512, which is the output of the first layer, and I go to 256. And then go to activation function. And then I go, my third layer goes from 256 input to 32 output, and then go through activation function. And lastly, my last layer goes from 32 input to just a single number. Remember, when I'm doing signal versus background classification, I only wanted to output a single number. So in this case, my neural network layer is outputting a single number for every single data point. And lastly, it goes through an activation function. So this is basically a structure of a full neural network that we can build. Yeah, question?
On the previous slide,
yeah.
My first question is, how do you choose the different weights? Like what do they depend on? And
how do you choose what?
The different weights.
Oh, the different weights. So the weights is actually not chosen. It's actually randomly initialized, and then it was updated during training. So that's what we're going to talk about in training, basically. Yeah.
One more question. Next slide. So you're going from like you're performing like 4 steps here. How is this different from using 4 different activation functions to go from 1000 to 1?
What do you mean using 4 different? Well, I mean, no, each layer can only input a single number. So this is kind of like a matrix multiplication, right? So it's like 1000 times 512. So it's like a single matrix that's multiplied through this dimension. So so you can, if you have a layer that's going from 1000 to 1, and you add an activation function to it, that's okay too. But that's just a single layer neural network. And it's very likely it's going to perform worse than this kind of deep neural network, because it has been shown that a deeper model performs better than a shallower model, basically.
Instead, if you use like 4 different activation functions instead of like 1 activation function.
Well, I mean, if you have 4, well, you can only have 1 activation function per layer. So if you want 4 you cannot use 4 different activation functions for a single layer. Remember, each layer is basically this neuron, right? So this neuron is the input multiplies by weight, and if you feed it into activation function. So there's no way to use 4 different activation functions for a single layer. But if you have 4 different activation functions for 4 layers, that's totally fine. Yeah, that's something up to you. You can decide.
And do you have to use the same activation functions every time for different layers, or can you use a different activation function?
Well, I guess I'm a little bit confused about your question. So activation function and the layer are paired. They are paired up, basically. Well, you can choose for each layer, you can have either 1 or 0 activation function. So yes, so it's not possible to have more than 1 activation function for a single layer. Yeah.
You're different layers in selective division.
Okay.
Yeah. Question?
I have like a question for the previous slide.
Okay.
So so when you get the weighted sum, I suppose that's like a single number, right?
Yeah, that's a single number.
What do you mean by fitted with a step function?
Oh yeah, I showed step function here, right? So the step function is basically, so the idea is this weighted sum, you have a single number. If this number is smaller than 0, your step function give you 0. If this number is larger than 0, your step function give you 1. Yeah. Yeah. We had another question there. Yeah.
Yeah, I was wondering about, I mean, you might answer this later, but how do you go about choosing which activation function is best suited to your model?
Yeah, so my answer to this question is generally is really arbitrary. So you can choose whatever you want. And so part of machine learning is, tuning your model is by choosing different activation functions and see which one works the best. So I think the only activation function that's really meaningful is the last activation function, which I'm going to talk about later when we are defining how to do different classification versus regression tasks. But for now, I would say for all the intermediate layers, the activation function is kind of arbitrary. It's not that important. Yeah.
Could you go back 1 slide, please?
Yeah.
I'm confused about why you can only have one activation function per layer, because for example, in the bottom right, the hidden layer, you have 4 neurons. Why can't I put a different activation function on each neuron?
Okay, so you are saying you are putting, okay, so you are, I guess technically you can, but I have never seen anyone doing that,
Okay,
basically.
alright,
Yeah, I guess that's my answer. Yeah, 'cause technically there's nothing really wrong with it, but it's just, people usually don't do that, yeah.
Yeah, so for the non-linear activation, I can understand for the step function, either rejected or like accepted. Can you
Yeah.
give me an example for the non-linear activation?
Okay, I'm gonna talk about it later, actually,
Okay, that's
yeah.
nice.
Okay, let's, yeah,
I assume that you are updating the weights through a feedback,
yeah.
like, is this a supervised training?
Yeah, so I'm gonna talk about how we update weights in training part. So yeah, later in the slides. Yes, for this problem we are setting up is a supervised learning, but again, I'm gonna talk about supervised learning in the task part, basically. Yeah, question?
One last annoying question for me. So on the next slide, you go and in all the hidden layer widths, they seem to be descending in size.
Yeah.
From 512 to 256.
Yeah.
32. Was that chosen arbitrarily or?
This is kind of like convention to make each layer smaller than the previous one. But you don't have to do this. So if you want the next layer to be larger than the previous one, that's fine too. But I would say generally the reason we want to make it smaller is we want to like condensate information because you know, in the input we have 1000 input, but not all of them are useful, right? For example, all of these are baseline noise, which are probably not that useful. So on the next layer, I want my model to kind of summarize this into a smaller number of representations instead of like having every single element.
Is there
So-
evidence that by making the layers smaller that it actually does condense the information?
Well, there are some study about that, yes, but unfortunately I'm not going through it today. So tomorrow you will hear a little bit about it. Yeah.
Okay.
Okay, I have to go fast. I guess I'm kind of running out of time. So try to keep your question until the end, unless you think it's very important. So thank you. I'm actually gonna break up. So we already built this neural network here. So I'm actually gonna break it up into 2 different parts. So the first part is going from the input all the way to this layer where I'll put 32 numbers. And I'm calling this my feature extractor network. So a feature extractor network, what it does is it takes your raw data, 1000 dimensional waveform, and it converts it into a lower dimensional, in our case, is a 32 dimensional vector, basically. And the rest is actually going to another part. So another part, which I'm going to talk about later. So now let's talk about how we can build our feature extraction network using some actual PyTorch code. So PyTorch has a module class, as you can see here, which you can use to build a neural network. So it's actually very simple. You can just use this sequential module to kind of stack layers together. So we can see the first. So first we want to initialize my neural network that's in the init function, which is very similar to the dataset function. And so it only called once when you are initializing your neural network object. And it actually you should define your neural network structure here. And here I'm going to talk about how we can define the network structure. So here in this end of sequential kind of function, you can just literally call each of the layers. So the first layer is a torch.end or linear layer, which takes a 1000 dimensional input and give a 212 dimensional output. So this is the first layer I showed you on the last slide. And so basically what you need to do here is just to tell the code what's your input dimension, what's your output dimension. And then we define an activation function that's following right after this linear layer. And the activation function, as I said, is adding nonlinearity to your neural network. And the most commonly used one is called rectified linear units. So this function is also very simple. You can see it has a boundary at 0. So actually basically before 0. So if your input to this activation function is smaller than 0, then it just give you a 0 back. But if your input to this function is larger than 0, it give you the original output, whatever it is. So this one is very commonly used in the machine learning community, but there are also other options, like for example, hyperbolic tangents, or even like a polynomial or exponential, anything you can think of, as long as it's not a linear function. So this is the init part of this module of this neural network object. So the second part is this forward function, which takes the input x. So x should be your input data. So in our case, it's going to be our waveform. And basically the idea is to feed data through your predefined neural network to obtain the desired output. So basically this is going to convert this 1000 inputs, input of batch size 1000 to output of batch size 1, right? So this is going to be called multiple times during your training and validation of the neural network. So make sure don't put anything that's very slow in this function. And you can see it actually return a value of x. Return a value we want to output here, which is stored in the variable x. So this is actually what we call the forward pass of a neural network. You do not have to understand what a forward pass is now, because I'm going to talk about this together with the backward pass in the training part of the neural network. This is basically my feature extraction network. So it's very simple. It converts a 1000 dimensional input, which is my waveform, into a 32 dimensional low dimensional vector. In our case, it's a 32 dimensional vector. And the next part I want to talk about is what I call the task module. So a task module is what defines what kind of task your neural network can actually do. So the task module actually contains two parts. One part is what I call the task layer. That is the last layer of my neural network. So the last layer here, it takes my 32 dimensional output I get from my feature extractor network, and it outputs just a single number, right? So the single number is either classification or regression for energy. So this task layer, yes, it produces. So the task layer, well, here for these two tasks I want to discuss today, I only need a single output, but of course, there are some cases where you want it to output multiple values. So the second important thing that I need in my task module is what we call the loss function. So a loss function will give you a quantitative measure that tells you how well your model, your algorithm can actually model your data set, can actually reproduce this ground truth, say PSD label low latency or the ground truth energy, we feed it into the neural network. So basically minimizing the loss function means your model is doing a better job. It means your model is reproducing your label, the label you gave it to you better. So that's what this gentleman was asking earlier, the idea of supervised learning, that you have some label that you use to guide the training of your machine learning model. And then I will start talking about task module by discussing about classification tasks. That's how we are separating our signal from backgrounds. So I want to start with a concept called information entropy from information theory. So how many of you have taken thermodynamics in your undergrad? So I guess almost everyone in the class, great. So basically, probably in the first several lectures, what you will learn from thermodynamics is this thing called Boltzmann entropy, which is basically calculated using this equation. So Boltzmann entropy contains two parts. First is the Boltzmann constant, and the second is this number W. Sometimes we use omega, like capitalize omega. So I was really confused when I first taken thermodynamics. I don't understand what this means. So the definition on Wikipedia tells me is the number of real microstates corresponding to a gas macrostate, basically. So the idea, so we have a very similar quantity in information theory that is called information entropy. So basically, it's defined by kind of this equation where your P is the probability of state I, and it's multiplied to a value log 1 over pi. So this 1 over pi quantity in information theory is called optimal coding length, but you don't need to understand it. It's some jargon that's we don't really care. The way you can think about it is the number of states in state I, assuming that all states have equal probability. For example, if you toss a fair coin, so you have two possible states, right? One is head, one is tail. So the probability for each of the states is 1/2. So if you do 1 over p, then that's 2, right? So that's the number of states that you can get out when you are tossing a fair coin. So this is a definition of information entropy. So here we will have a quantity called binary entropy. That is exactly the situation. That is information entropy that we can get when we only have two possible states. So when you're tossing a coin, you can either get only head or tail. So if you write it out, the equation of information entropy like this, you will get this kind of equation where you have p times log 1 over p minus 1 minus p. So that's the possibility of the other state times log 1 over 1 minus p. So let's try to understand what this binary entropy is actually telling you. So suppose you are tossing a fair coin, which means the probability of getting a head and tail are the same. So basically, you can calculate this quantity by plugging in just into this equation because the probability of H and T are the same. Your P is just 1/2, right? So if you calculate this, you get a value at 0.931. So this value is pretty high, right? But suppose you are tossing an unfair coin. If your coin is not fair, the probability of getting H and T are different. Let's say your probability of getting a head is 0.8, and the probability of getting a tail is only 0.2. So if you plug this value into the binary entropy equation, your binary entropy is now at 0.5, which is smaller than 0.69, right? This is 0.7, this is 0.5. So when you have an unfair coin, your entropy is actually decreasing. So this is because information entropy can be considered as the average amount of surprise or surprisal that we can measure from the system. So when you are tossing a fair coin and I'm asking you what would be the possible outcomes, you will say, I don't know, it can be either a head or tail. I have no idea, right? So it's hard to predict the outcome. So the average amount of surprisal is high. So it's very likely that I predict it's going to be a head, it's giving me a tail, and the vice versa. So the average amount of surprisal is very high, and therefore the entropy measure is also high. For an unfair coin, so if I tell you the coin has 80% of probability to get a head, so in this case, the outcome is very likely to be a head. So if I predict the outcome to be a head and I get a head, I'm not too surprised, right? So the average amount of surprisal is low, and therefore I have a lower entropy. So this is a very useful concept that we can use to build the loss function of my machine learning classification model. The other concept I want to talk about is cross entropy. So cross entropy is actually calculated over two probability distributions. So previously, when we are talking about binary entropy, we are just talking about a single probability, right? Like tossing a coin and it has a fixed probability. But here we are actually talking about two different probability distribution, Px and Qx. So, and cross entropy was calculated almost exactly the same form as how we are defining the entropy. And so suppose we have a classification task to separate our neutrino signals from the Majorana demonstrator from the background we want to reject. So the ground truth distribution would be our Px. So that would follow the distribution of my labels, right? Now my label are just a whole bunch of 1 and 0s. So, but that 1 of 0 follows some kind of underlying probability distribution. So in this case, this is my Px, the Px I want to approximate. So on the other hand, we can build a neural network and it outputs a single value for every single waveform. And so it analyzes every single waveform and produce the output distribution Qx. So this is the distribution of your neural network output. So basically, what we want to do is by minimizing this cross entropy, actually, let me talk about that on the next slide. So there are two types of entropy that we can minimize. One is combining the cross entropy with the binary entropy I talked about on the last slide. So basically, in the binary entropy case, you can only get two possible output. Event is either a signal or a background. So it's calculated like this way, as you can see here. But there is also cases where you can have n different kind of possible output, right? When you have a neutrino, is it a muon neutrino, electron neutrino, tau neutrino? So in this case, you can have multiple different classes, and this is like a general cross entropy. So you can see binary cross entropy is basically a special case of general cross entropy. So I told you information theory, information entropy measures the average amount of surprisal that we have in our data. So cross entropy measures the average amount of surprise from your neural network output distribution Qx, given that the ground truth distribution follows some kind of distribution Tx, and we get our ground truth distribution from the label, right? So we have this label. So basically, when we define our cross entropy loss, we are minimizing the cross entropy. Minimizing the cross entropy is identical to minimizing the surprise of your neural network output Qx with respect to the ground truth label. So that means when my inputs, when my ground truth tell me, my label tells me my input waveform is a neutrino, my neural network should unsurprisingly tell me my input is a neutrino, right? When my input waveform is a background event, is electron noise, my neural network should unsurprisingly tell me that this is the background. So that's why when we are lowering our cross entropy loss, it means we have a better separation between our neutrino signal and background. So let me try to take some questions and see if there's any before I move to the next section. Any questions? Yeah.
So just for clarification, on the cross entropy equation, the sums over all the like xi.
Yes, so this should actually be an integral. So if it's a continuous probability, it should be an integral. If it's discrete, if it's multiple possible classes, then it's a sum. Yeah. Okay, great. So then let's move over to how we are actually defining our task model. So remember, I said task model contains two parts. One is a task layer, which is the last layer of your neural network. And the layer actually contains the neural network layer, which converts, the 32-dimensional vector to a single number plus activation function. And the second component of the task module is the loss function. So the loss function, I just described what is the cross entropy loss. And so given this, we can actually set up different kind of classification tasks. So the way we can set up our first binary classification task is ask your task layer to output just a single number. So this number is going to be one float point number between -infinity and infinity. So your neural network is free to give you a number in any kind of range. So whatever it likes. So after training, this can be considered as what we call the classification score. So if this score is higher, it means your neural network think the answer is more likely yes, or your input waveform is more likely a signal. If the classification score is lower, it means the answer is more likely no, and your neural network is saying this event is more likely to be a background. Given this configuration, you have to set up a threshold to distinguish your answer from yes or no. You can say, I set my threshold as, let's say, 0.5. So if the score is above 0.5, I say the answer is yes. If the threshold is below 0.5, I say the answer is no. So you also need the activation function. So in this case, we are using what we call the sigmoid function, torch.sigmoid. So the sigmoid function expression is shown here. So basically what it does is that it takes the input from any range from -infinity to infinity, and it outputs a single number from 0 and 1. So the sigmoid function can output something that's more like a probability, right? So I can, after the sigmoid function, I can interpret my classification score as a probability. So this event is 90% likely to be a signal, 10% likely to be a background. And the loss function I'm going to use is a binary cross entropy loss that I just discussed. So this torch.n.bce loss function. So this function only takes input. Its input has to be a number between 0 and 1, which after we feed it into the sigmoid function, it actually satisfies this constraint, right? Because my sigmoid function only output values between 0 and 1. And its target has to be either 0 or 1. It can only be these two numbers. But the good news is that my label is exactly either 0 or 1. So that's what provided in the data set, and it cannot be other numbers. So this is the first way to do binary classification. So there is a second way, which is actually very similar to binary classification number 1. So the only difference is here. First, now I deleted my activation function. I'm no longer using this sigmoid function to map my output from -infinity to infinity to 0 and 1. And I'm using a slightly different loss function called BCE with logis loss. So for this loss, its input does not have to be between 0 and 1, but it can be any range between -infinity and infinity. So it's very similar to the first kind of setup. So it's basically the same thing. So the only difference is now your score doesn't have to be between 0 and 1. It can be any range from -infinity to infinity. So there is another way to do binary classification. So the idea is ask your task layer, the last layer of your neural network to output two numbers instead of a single number. So this would be two float point number between -infinity and infinity. And so after training, this two number can be considered as what we call the classification decision. Basically, what we need to do is we need to assign a meaning to this two number, right? I say the first number corresponds to the answer to be yes. The second number corresponds to the answer to be no. And the larger number of the two will actually represent the one I select. So if the first number is larger, I'm saying my decision is yes. And if the second number is larger, I say my decision is no. And I do not need the activation function for this case. And the loss function I'm going to use in the code is called torch.n.cross entropy loss. So this is the one I'm going to use. So lastly, we can also do multi-class classification. If we have multiple classes, instead of just answering a yes or no question, in this case, it's a very straightforward generalization from this binary classification 3 category. And what you do is basically you are just converting this number 2 to a number n, as you can see here. So basically is a classification decision among different amount of classes, and you just choose the class with the largest output. So the second task I will talk about is regression. So what if you want your neural network to reconstruct the energy of the input waveforms? So in this case, your task layer should also output a single number. So the number should be between -infinity to infinity. So it can be, so your sigmoid, your activation function is something you can choose. So if you wanted to reconstruct energy, then you probably don't want activation function because because your energy can be any value, right? It can be 0, can be 1,000, 2,000. But if you want to model something like a neutron capture efficiency or some kind of efficiency, you know your efficiency can only vary between 0 and 1, then you can feed it into a sigmoid function. So for loss function, you should just use the mean square error loss, which is plotted like this. So it's actually very easy. You just take your neural network output minus the energy and you square them. And so this is the most commonly used. And yeah, so let me skip this part about discussing gradients. So the other function you can use is the L1 loss. So L1 loss is basically the absolute decision, the absolute distance between your neural network output and your energy label. So you can see here you are pulling your task layer output minus the energy, and you just add a absolute value sign around it. So you can see how this L1 loss looks like is like this. So it's very flat in both the positive and negative part, but it has this very sharp kink at 0, which might be causing problem when we are training our neural network. So yeah, question.
So I'm just curious, if you make the loss function to preserve the sign of the difference, can you use that to tell it like which direction it needs to move?
Yeah, the thing is that we want our loss function to be something that when we minimize it, it gives you a better performance. But if you're preserve the sign, then your model is going to be keep minimizing your loss function to a very large negative value, right? And it does not reflect the performance of neural network well. So that's why we want it to be either squared or taking an absolute value. Yeah. So there is a way where you can combine this MSE loss and L1 loss. That is, when this value is smaller, when it's entering this region where it's likely to have this kink, we do MSE, and when it's further away, we do L1. So this is what we call the smooth L1 loss. So how can you code this task module into a neural network? So we already discussed how we are coding feature extractor. So here we also have, we can see we have the task layer, which output a single number. And we also have the activation function, but since here I'm doing energy regression, I am omitting the activation function. But if you need, you can add any activation function here. So this is my neural network class, and after that I can initialize my neural network as an object, as you can see here. And I also initialize my loss function. Here I'm initializing a L1 loss. And what I'm doing here is I'm feeding my neural network into my regressor. I'm feeding away from into my regressor neural network object. So it passes through this forward to return a single value, as you can see here. So that's my output. And then I'm feeding both the output and the energy. So the energy is a label I get into this loss criteria to get my loss value. And then I can, when I'm training, I can optimize this loss. I can reduce this loss. So you can replace the task layer, the activation function, and the loss function to anything you just learned from the previous kind of templates to achieve your own task, either classification or regression. Okay, now let's go to the training part of the neural network. I have about 30 minutes. I hope I can finish everything. So training of a neural network is what we call the gradient descent optimization process. So basically the idea is if you want to find the max, if you want to find the value of x that maximize the function fx, we can do this by calculating the gradient with respect to the function of the function fx. And then we are moving x in the opposite direction of the gradient. So x prime, the next step of my x is equal to x minus gamma times the gradient of the function fx. And gamma is what we call the learning rate of a gradient descent algorithm. So let me give you an example on the right. So you can see here, the dashed blue line is a function I want to minimize over. So that's fx equal to 1/2 x squared. So very simple second order polynomial function. So its derivative, which is its gradient in one dimension, is basically a straight line, right? That's this green line function. So if my current x is located here, so it's smaller than 0, our gradient the derivative is also smaller than 0, right? So I want to move x in the opposite direction of my gradient, which is the positive direction. So my x will go in this direction like this to the right. So we can decrease my function f by moving x to the right. And if I have x greater than 0, if my x is at this location, we have its derivative, so the gradient to be greater than 0. So I can decrease f by moving to the left. So this is how gradient descent works as a very simple algorithm. So now let's go back to our neural network. So basically, remember our neural network is basically a function. So let's say here I have a 2-layer neural network. So for the first layer, I have a set of weight alpha multiplied to my input x plus a single number, which is bias. And on the second layer, I have the output of my first layer, and I multiply it by beta, which is the second set of weights, plus bias, which is a single number. So here, in this case, my alpha and beta, so those weights I multiplied to either the input or the output of the first layer are weight matrices of the neuron, and their value can change during training. So this is also sometimes we call the kernel of the neural network. So the idea of training a neural network is to find the best set of this kind of weights or the kernel that we multiply to either the input or the output of the previous layer to best fulfill my classification and regression tasks. So this is pretty much the problem of gradient descent, right? We have some value of weights, and we have some value of weight we want to minimize a certain objective. That's the loss function that we have. So training neural network is equal to optimizing the kernel parameter with respect to the loss function. So we want to find the kernel parameter, the weight that best minimize my loss function. So to do this, we can, is this auto power or something? I will just use this probably. So to calculate this, to calculate this, we will just calculate the gradient, and this is a very important step that we need to do to optimize these parameters. However, when we are calculating the gradient for a neural network, we need to calculate over the entire data set. So this is a big problem because does it work now? Oh, great, thank you. This is a big problem for current generation experiment because in current generation we want to train our neural network with 1 million data. So if we do, so that means when we are doing gradient descent, we need to calculate the gradient over like 1 million data points. Like every single time we want to move my model, we want to move for one step. Yeah.
Could you explain the notation of M and K and alpha M and beta K?
Oh, that just means different indices of the input basically. And also, so M means M is basically between 0 and 1000 because my waveform has 1000 value, and the K is basically the second layer, so it's between 0 and 512 because my second layer has the input of 512 and the output 256, right? So yeah. One of the major kind of invention that's made training neural network over large data possible is what we call the stochastic gradient descent. So the idea is break your training data into smaller batches, as I mentioned earlier in the lecture, and each batch has to be randomly sampled from your data set. This is very important. If you do not randomly sample, your neural network will not train. So in this case, the size of your batch, so how many data you group into a batch is the hyperparameter of your neural network model that you can choose from. And the weight of your model, your alpha and beta are updated kind of stepwise by sequentially feeding each batch into your model. So you don't have to do gradient descent over the entire data set, but you can just do it batch by batch. So this will reduce the effect of training using all data simultaneously. And this is possible because gradient descent operation is an expectation value, but I'm not going to talk about the math behind this. So now, given all of this, we can kind of put our neural network into a setup, so into a forward, backward kind of setup. So we have an input, we feed into my neural network model. So input is X, we feed into neural network model X, X as the input, and I have the weight parameter alpha and beta, and it gives me a prediction, right? It gives me either a classification decision, a classification score, or energy. That's my Y hat. And then, so this is a forward path. So feeding the data through your neural network is a forward path that I already kind of showed you in the code part. And then we want to go to the backward path. So that is calculating the loss between my neural network prediction y hat and my actual label, actual energy, or actual signal versus background 0 or 1 value using the loss function, either cross entropy loss or MSE loss or L1 loss. And then I calculate the gradients with respect to each of this kind of weight kernel parameter based on my loss value. And eventually I use my gradient to update my kernel to do the x prime is equal to x minus gamma times gradient part. So basically the forward pass is to produce y hat, my neural network prediction from input x and the kernel parameter alpha beta. And the backward pass includes calculate loss, calculate the gradients using what we call the back propagation, which we will talk about in the next few slides. And we update our weight or our kernel by this gradient descent, stochastic gradient descent algorithm. So how can we actually calculate gradient? So thinking about your neural network as a multi-layer, very complex function. So we can actually just use chain rule to calculate the gradients. So my neural network is its input is x, is a 1000 dimensional waveform, and each layer can be considered a function f1, f2, all the way to fl. So we can kind of unroll this, right? So the output y is equal to fl times xl, and xl is equal to fl minus 1 times xl minus 1, and all the way to where x1 is equal to f1, my first layer, times the raw input, my raw waveform x1. So we want to compute the derivative dy dxl throughout this very complicated function for all the L's, for all my layers. So I can draw this as kind of a diagram. I have y, xl minus 1, all the way to the bottom, all the way to x1. So the way I can do this is if I want to calculate dy dxl, so the first derivative I can calculate is dy dxl, then dy dxl minus 1 is dy dxl times dxl minus 1, right? So it's very simple chain rule that you learn in first year calculus. So the good news about this is you can keep going, and every step, so when you want to calculate dy dxl minus 1, you can actually reuse what you calculated previously, right? So you already calculated dy dxl here, and then dy dxl minus 1 is just dy dxl times dxl minus 1. So you can keep kind of moving forward along this kind of diagram that I draw here. So this diagram is actually very, I would say, very useful in building a neural network, and is actually what we call the computation graph. So a computation graph is a directed graph where each node we have operation, either plus, minus, or some kind of function. So for example, if you have this function, y equal to sine w1x plus log x plus cosine x, you can actually break it up into a computation graph like this. Like you have x, you do log, and you also do w1 times x here, and here you have addition notation. You add them up here, and you feed them into a sine function, and also you feed your x into a cosine function, and you add them up together, you have your y. So this is how we are breaking this equation into a computational graph. So the deep neural network is very complicated, but it also can be broken down into a computational graph. So this means you can calculate gradient along these graphs. So basically how you are doing this is what we call a backpropagation equation. So you can calculate gradient with respect to each of the weight kernel parameters. So the idea is you start from your loss function, which you put in your forward pass, you calculate the loss, right? You already know what it is with respect to your label or the target you want to produce. And you can move along the computation graph. So when you are calculating your loss with respect to the weight of the first layer, DL, DWL, what you do is you calculate first DL with respect to DXL, and then you calculate DXL over this node, the sum over node DSL, and then you calculate DSL over WL. So you just move along this computational graph to compute the loss. And if you have one more layer, you can reuse the previous result you calculated up to here, and then you just move one step further. In this way, you can calculate the derivative of your loss with respect to your parameter, your kernel, your weight parameter WL minus 1. So I have been spending a lot of time discussing how to do this, but you will see it's actually very simple to actually code it in a neural network. So here is how you can actually train a neural network. So we first set up our model. In this case, I'm doing a classification. So my model is classifier. My loss function criterion, for classification is binary cross entropy loss. And optimizer, you can use SGD optimizer, but I really recommend using Atom optimizer, which I'm not going to discuss in too much detail. But it's very common choice for building a machine learning model. And here, basically, you want to loop through your data. So you have a data set, let's say you have 10,000 data points. You want to train through it multiple times. You don't want to just train through it one time. So the number of iterations, the number of time you want to train through the entire data set is called epoch. So we define nested for loop where the outer layer is the epoch, basically, and the inner layer, we are basically iterating through the train loader. So the train loader is going to spit out waveform, labels, and energies for each batch, right? Remember, we defined the batch size before. So each time is spit out a batch of waveform, a batch of label, the batch of energy that all correspond to each other. So here we have the forward pass where we feed our data, the waveform, through my classifier model, and I produce a single number as my output. And then I feed my output and label into my criterion, into my loss function to calculate the actual loss. And here is the beauty. So backpropagation, so everything I discussed in slide 28 to 35 with a lot of equations can be done in a single line. So that is this line, lost or backward. So you don't need to do anything. You don't need to code any of the gradient calculation. You just call this line and it do the gradient for you. So it's very easy. So lastly, this line is, so now we calculate the gradient. This line actually updates the model parameters according to the gradient that we calculated with respect to each of the weights. And lastly, we want to zero the gradient we accumulated on all of our weights so that when we go to the next step of our for loop for the new batch of data, is not like keep accumulating the old gradient. Okay, so next one, I'm going to evaluation. So any questions about training? Let's see, yeah.
So the epochs, are those the same 70%? You're looking at the entire data set every time?
Yeah. So let's say if my epoch is 30, then I'm training over the same 70% data set like 30 times. Okay. So you don't want to train it only through it only once. You don't want to train through it multiple times. Yeah. Yeah.
For stochastic gradient descent,
Yeah.
I'm assuming the original order of waveforms in your data set isn't necessarily correlated. So why do you have to randomly pick?
Yeah, that's well, okay. So the idea of yeah, that's a very interesting question. So the idea of gradient, stochastic gradient descent, I would say for let's use classification task as an example. So the idea of stochastic gradient descent is that each batch of a data set cannot only have pure signal or pure background. So if all your batches are signals or all your batches are backgrounds, then that's not going to work. It has to contain a mixture of signal and background. So the exact reason why that has to be the case is based on the statistical calculation. It's based on the calculation of the expected value. So you basically want each of your batch to be somewhat a good representation of the entire data set. So that's why we have to do random sampling. It can't be like all signal or all background. Otherwise, your neural network will be biased. Question?
How do you determine the number of epochs you want it to have?
Yeah, that's a good question, but unfortunately, I'm not talking about it today. So, yeah. So, okay. Yeah. So, I would say at the beginning, if you want to start building a neural network as a beginner, just choose your favorite number, like 30, 50, whatever. If you are more advanced, it's possible to use some kind of mechanism to kind of define like when you should stop. It's called like early stopping mechanism. So it's basically monitoring the performance of your neural network until it stops improving. So this is a common way of kind of automatically choosing a number of epochs. Yeah.
When you're minimizing the loss function, how do you avoid getting trapped at the local minimum?
Yeah, so my answer is there's no way you can completely avoid getting trapped into local minimum. I would say getting trapped into a local minimum is not necessarily a bad thing. So actually most of the neural network, when they are trained, they are not at the global minimum. There are some work, like theoretical work, which tells you if you modify your neural network structure this way, you can turn a local minimum into a global minimum, but I think they are rarely used. So I guess my answer is we really don't consider that. We really don't consider like a guarantee that's something that guarantee you to always go to global minimum. Yeah, as long as it works. So it all depends on evaluation, right? It all depends on how you are evaluating your model. So if your model is doing good enough job for whatever you want to do, signal background classification and anti-regression, then that's good. So you don't need to worry about whether it's actually at the global minimum or not. Yeah. Let's leave all the questions to the end because I'm almost done and I have very little time. So, okay, so now I want to talk about how we can evaluate. So now we have our entire model, we have our model trained, and we want to know how well it works. So the first concept I will discuss is underfitting versus overfitting. So underfitting occurs when your model cannot adequately capture the underlying structure of the data. So for example, if you're fitting a model to this black dots, as you can see here, so underfitting case would be if you are fitting a red line into your data. So you can see it doesn't really capture the little trend that's happening in your data, right? So this is the underfitting case. So overfitting case is the reverse. So that's your model are correspond too closely or exactly to the training data, but it fails to generalize to the things outside your training data. For example, in this case, you can see your model is fitting your data like perfectly, right? It's like a string that goes through every single bit of my data set. So my loss is basically 0. But now if I pull out a new data point, let's say this red data point, you can see it's actually doing a pretty bad job. So it's not going through a data point that it has not seen before. So overfitting is a major problem that people usually encounter in machine learning, especially in training a neural network, because neural network is a very, very powerful model and it's very easy for it to overfit. So a good fitting would be something like this. So you can see a good fitting is this kind of second order polynomial, which captures the overall trend of the data set. And if I pull out a new data point, it's relatively close to the value that my model is predicting. So you can see how the effect of underfitting versus overfitting looks like. So you can measure the error of your neural network with respect to the number of epochs you are training. So you can see in your training data set, your errors just keep decreasing like this. But if you are looking at the validation data set, which is not part of the training, remember we discussed about the train loader versus validation loader. So validation loader are the data set that the neural network was not trained upon, it has not seen before. You can see the errors start to decrease. That's the region where you're underfitting your data, you are doing better and better. But there is another point where your error on the training set is decreasing, but the error on the validation set start to increase. So this is when you start to overfit your data set. And that's something we want to kind of avoid. So one way to mitigate overfitting effect is using something called a dropout layer. So during training, what dropout does is randomly set some of the neuron to 0, which forces the neural network not to become solely dependent on one neuron. And it has been shown that this is the cause of overfitting for many of the times. So dropout layer is very easy to implement. You just do torch.end or dropout after your activation function, as you can see here. So you just insert it into your neural network model. And the idea of dropout is also kind of like ensemble learning. So you are training, so every single time, if you drop out some, so this is a random process. So every single time you randomly drop out some of the neurons. So that's equivalent to kind of like a new model, right? And then eventually you are averaging all your randomly dropped out model into a model that outputs a result. So this makes the training more robust and mitigate the effect of overfitting. So lastly, I want to discuss how you can quantify how well. So now we build a classifier, we feed it through the feature extraction network. We use the binary classification 1 task module to output score for every single waveform. And it's a float point number between 0 and 1. And if the higher score means it's more likely yes, lower score means more likely no. So how can I know how well my neural network model is doing in terms of classifying signal from background? So, so this is the setup of the problem. So in classifying the Majorana demonstrator waveform, we have our signal, which is also called positive events. That's the single side waveform I showed you at the beginning of the class. I hope you still remember what is the single side, what is the multi-side. So for the background, which is also what we call the negatives, those are the multi-side waveform that we showed. So let's say lambda is the classification score that a neural network produce for each of the input waveform. And lastly, as I said, I need to set a cutting threshold, right? So let's choose a number, let's say 0.5. So let's say if my lambda is greater than 0.5, I'm calling this input waveform to be a signal. If my lambda is smaller than 0.5, I'm calling this input waveform as a background. So here, basically, I have a table that's drawn on the right. So this is classified as signal. That means your neural network output is smaller than 0.5. larger than 0.5, and classified as a background means your output is greater than, your neural network output is smaller than 0.5. And on the column, I have my true signal versus true background. So that's what my PSD label A versus Z, like what's come with the data tells me. Is this an actual signal or is this actual background? So given this table setup, I have 4 different entries, right? I have my true positive, false negative, and true negative here. So I will explain what this means using this kind of fill in the blank sentence. So it's like blank means this event is blankly classified as blank. So what does this mean? You just fill this word into the sentence. So true positive means this event is truly classified as positive. False positive means this event is falsely classified as positive, which means it's actually a negative, but it was classified as positive, right? True negative means this event is truly classified as negative, and false negative means this event is falsely classified as negative. So given this definition, I can actually calculate 2 concepts. One is called true positive rate. That is my true positive divided by true positive plus false negative. So what does true positive plus false negative mean? Is a total number of actual signal events in my data set, right? That's the first column, which is the number of events where my PSD label A versus C tell me it is actually a signal. So TP divided by the number of signal events in my data set. And false positive rate is false positive divided by false positive plus true negative. So similarly, FP plus TN is the second column, which is the total number of true background events in my data set. So I can obtain it by just looking at the PSD label A versus D that comes with my data set. Basically, the problem is that these 2 values, true positive rate and false positive rate, are not really a good metric to monitor the performance of your neural network classifier. Why? Because it actually depends on the cutting threshold that you select. So for example, here I said I'm building a classifier which assigns a score to my signal and background events, and I can plot their score as a histogram, as you can see here. So, and I'm making a cutting threshold at 0.5, which is this red dashed line, and I'm calling everything about 0.5 to be my signal, and I'm calling everything about below 0.5 to be my background. The thing is that now if I change my mind, I want to set a different cutting threshold. Now I move my cutting threshold from 0.5 to 0.2, then my true positive is increasing, right? It's increasing by this portion. So those are the amount of signal that's additionally got classified as signal. And my false positive is actually decreasing, right? So this amount of signal was additionally classified. This amount of background was additionally classified as signal. So my model did not change at all. So for the same events, my model is producing the same classification score for every single event, but by simply changing my cutting threshold, I'm changing my true positive rate and false positive rate. So this is actually pretty bad. We need a threshold independent metric we can use to measure the performance, the actual performance of my model. And this metric is defined from the receiver operating characteristic of the raw curve. So the idea of the raw curve is to evaluate your model at all the possible thresholds that you can make a cut. So let's say now I still have my neural network score, the prediction of my neural network here. So what I'm gonna do first is I'm gonna cut at a value of -0.1. Well, maybe you'll ask, your neural network can only output a number between 0 and 1. So what's the point of cutting at -0.1? So if I'm cutting at -0.1, it means I'm accepting every single waveform as a signal, right? So in this case, my true positive rate is 100% because every single signal event got accepted as a signal. But at the same time, my false positive rate is 100% as well because every single background got accepted as a signal as well, right? So in this case, if I'm plotting my true positive rates on the y-axis versus false positive rate on the x-axis, I have this dot, right? So basically, all the receiver operating characteristic of the raw curve start at 1.1. So all the curve will have this will start at this location with 100% true positive and 100% false positive. If I move my cutting threshold to 0.2, my true positive rate decreased, right? It decreased to 87%, and the false positive rate also decreased to 24%. And I'm plotting this on this plot on the right as well. So this point is here. And I'm further moving up my cutting threshold. My true positive rate decreased. My false positive rate also decreased. and that's a new point. And then I'm making another cut at 0.8. So this is my new true positive versus false positive, and is being made here. And lastly, I can make a cut at 1.1. So if I make a cut at 1.1, I'm basically rejecting every single event in my data set, right? So if you do this, your true positive rate is 0 because you are rejecting every single signal as background, but your false positive rate is also 0 because you correctly rejected every single background. So this will end up as a 0.00 on this true positive rate versus false positive rate plot. And so basically all the raw curve you make, regardless of kind of what kind of model you are using, will always end at 0, 0, and 1, 1. So the raw curve will always start at this position and end at this position, and is really so what's really different is how this curve was drawn for different kind of classification tasks. So a perfect raw curve would be something like this, like a upper right kind of right corner. So that means you have 100% of true positive rates at 0% of false positive rate. And if you calculate the area under this curve, it's going to be 1. So that means every event is classified correctly, basically. So this case is only possible if you randomly select an event, a signal will always have a score greater than a background event. So the worst raw curve you can make is this straight line that directly connects 0, 0 to 1, 1. So at every single point, your true positive rate is equal to your false positive rate, and your area on the curve is 0.5. So this is the same as just by classifying by tossing a coin. So if your coin is head, you classify it as signal. If your coin give you tail, you classify it as background. So it has nothing to do with the data. So this is the worst you can do. So there's another case where your raw curve is going like this. So this is what I call the anti-perfect raw curve. So in this case, you are classifying every single event wrong, right? So your true positive rate is 0, your false positive rate is 100, and your area on the curve is 0. But if you are doing everything wrong, it means you know the right answer, right? You can just reverse the label and then you will turn this into this. So that's why I call this an anti-perfect raw curve, because it actually means you know everything, but you intentionally do it wrong, basically. So the area on the curve that we just described actually has a statistical meaning. Is equal to the probability that a model will rank a randomly chosen signal. So if you randomly get a signal event from a data set and you randomly get the background events from your data set, it's gonna rank the randomly chosen signal to have a higher score than a randomly chosen background. So if your model is perfect, no matter, when you randomly choose a signal, its score is always going to be higher than the background. If your model is the worst, is like random classification, then if you randomly choose a signal, the probability that it has a score higher than the background is going to be 50%, right? Because you are just assigning a score by tossing a coin. So this is the statistical meaning of the area on the curve of the raw curve. Okay, I finished barely on time. So give me 5 more minutes to kind of review. It's a lot of information, I totally understand. So I don't expect you to understand everything from my past, but all my slides and lecture notes are going to be posted. So please, if you want, please go through it yourself and try to digest a little bit to understand. This information are very important to understand the lecture tomorrow. So let's do a very quick review. So in the data processing side, I discussed about the Marana demonstrator data and how to build a PyTorch data set and how to do your data processing to kind of change the shape of your waveform, and also how to create the data loader by wrapping your dataset objects into this data loader class. And in the feature extractor part, I discussed about neural network, linear layer activation function, how to create a simple neural network in PyTorch, and also what is a forward task look like in your neural network. So in classification, I discussed about the task module, which contains the task layer, which is the last layer of your neural network, plus the activation function, plus the loss function. So remember the activation function of the last layer of your neural network is actually meaningful because it needs to kind of be coupled with the loss function to do different kind of tasks. We also discussed about cross entropy and binary multi-class classification. For regression, I discussed different kind of loss, MSE loss, L1 loss, and smooth L1 loss. For training, I discussed stochastic gradient descent, backward path, and how you can do this by building a computational graph. And to implement PyTorch is just one line of code. So it's very easy. Well, a lot of theoretical background within it, but actually when you are actually doing it in PyTorch, it's very easy. So lastly, in evaluation, I discussed about overfitting versus underfitting. And we also discussed about ROC analysis, which can allow you to evaluate the performance of your model without depending on the actual cutting threshold that you select. And so I actually did not really discuss about regression evaluation. Sorry, I deleted it from the slide, which is good because now I'm right on time. Lastly, I want to post some very useful links. So all the lecture materials are going to be posted into this Google Drive. And I also write a Jupyter notebook code that include all the PyTorch code that I kind of showed you today into a single concrete kind of project that allow you to download and analyze my random demonstrator data. So to produce the classification result that I showed you in the lecture. So I also want to put some link about the possible machine learning classes that you can take a look to get more information. For example, if you're interested in how to mathematically derive linear regression, look at some of this. So the first two courses were actually taught by me. So the first course was designed by me, and it was kind of mainly focused on time series analysis for germanium detector. So, but if your experiment is also producing time series, you can look at this. So the second course was taught by me and a few other computer scientists, friend of mine. So it contains a more kind of computer science touch of machine learning. So they are actually analyzing image of cats and dogs instead of physics detector data. There's also this very famous MIT course, 6S191. So I actually learned machine learning 5-6 years ago from this course. So it's a very nice intro course, and also this very famous course called deep learning specialization. And also I put my website and email address here. So thank you for your attention, and I'm happy to take any questions. Maybe this gentleman, yeah.
So this might be super naive from me, but I guess it kind of seems like you're just building a model with like a bunch of different parameters, and then we're just fitting that model to the data many times. I guess it's kind of like a different algorithm to do it. I don't know if that's accurate.
Well, I think you catch probably 80%. Fit. Yeah, but it's not actually a fitting process. It's this training process that we discussed using backpropagation, stochastic gradient descent, right? So I guess it's slightly different from fitting, but to some extent, yes. I think you are getting most part of it correct. So I think we had another question. Yeah.
Yeah. Is the point of the area under the graph curve? Yeah. You want to maximize the area?
Yes. If you remember this, what did I do? Let me play it. Yeah, so if you remember this plot, yes, so the area on the curve of 1 is the best you can get, right? And the area on the curve of 0.5 is the worst you can get. So basically you want to get a value as large as possible when you're training a model. When you are evaluating the model, you don't train on this, but you evaluate on this. Yes. I think we'll have another question here. Yeah.
Yeah.
Okay.
You can go. I was wondering, so with respect to training on data that has already been classified with another algorithm, like in this example, or with another process, is it then the case that you can't, with a neural network, do better, for example, in terms of signal detection efficiency for the experiment than with the original algorithm, but you get better computational efficiency when you're running it? Like, if you already have another algorithm to classify, how do you think of the value of then training machine?
Okay, that's a very good question, which I'm going to address in tomorrow's lecture. So what I'm showing you today is mainly building neural network based on some of the data that has already been very well analyzed by Walter and I and Anna and our collaborators. So it's not creating anything new, pretty much. We are trying to build a neural network to best mimic the existing performance of the Marana demonstrator and as a tip, basically. But machine learning is definitely more than that. So in tomorrow, we will discuss about approach where you do not have this label. So you only have the data, but you do not know what they actually are. So what you can do with them. So and tomorrow's lecture, I'm personally very excited about it because I spent a lot of time thinking about how to make tomorrow's lecture. So it actually tells you all the different kind of things you can do using machine learning. Well, with very little detail, because today I can give you a lot of detail about how to write the code, but tomorrow I just don't have enough time to give you the detail. So I'm only going to kind of tell you all different kind of things that machine learning can do. So I think your question will be better answered tomorrow. So yeah. Sorry, I think we have a question there.
What is the sign of overfitting? Like your loss function goes to zero very quickly after one epoch or two?
Well, yeah, of course, if your loss function go to zero very quickly, that's a very clear sign of overfitting. But usually the way we are monitoring this is to have two data sets, one training data set and one validation data set, right? So if you observe something like this, so your loss is keep decreasing on the training data set, but your loss start to rise on the validation data set, then that's a sign of overfitting.
Okay, so is it a good practice like to confuse your label, like to put some mislabel in, if you are doing binary classification, for example, can you get 10% confusion in your labels?
Could you repeat? So,
Like for example, let's say that you are doing binary classification.
yeah.
And you have two labels, so you can get some of the second label little bit in the first label to make intentionally a confusing.
I see. So I think you are talking about something called label smoothing, which I'm actually not going to cover. So this is a more advanced technique for your machine learning to kind of optimize your machine learning model. Yeah, so I think that's one way you can do this. But overfitting is actually, I would say, is not a very big problem because there are many different ways to avoid this. Actually, like for example, dropout is one way, and the early stopping method that I mentioned is another way. So you just keep monitoring its performance over the loss, and you find a point where it stops decreasing on the validation data set. So and you just stop your model here, and you don't train forward. So that's another way to mitigate overfitting. So the label smoothing, I think, is another, as you said, is another way that can do this. Yeah. I think we have a question here. Yeah.
Actually, a follow-up of that question.
Okay.
So I think machine learning network can have some kind of interpreting of the problem, like order analysis we did before.
You mean like interpretability or?
Yeah. So my question is, do we have any related research about the interpreting of the network we use for an experiment?
That's a topic for tomorrow's lecture, actually. So in tomorrow's lecture, I'm discussing about interpretability of the neural network. Yes, so you'll hear about it tomorrow.
So in a sense, I imagine that if for processing this data, there's some global optimal neural network that would do this as best as possible.
Processing, do you mean data pre-processing or the actual model?
The actual model.
Okay,
There was some global optimal model.
You mean the global minimum of the loss function, or?
Some global minimum, I mean, just some perfect configuration of all the weights and all the activation functions such that you have the best rock curve.
Yeah, sure.
How can you tell how close you are to that? What that optimal rock curve could possibly look like? Because I mean, I don't know, how do you know your model is good, and when should I stop training my model over and over again? Okay, so that's actually two different questions. So if you're asking when should you stop training your model, I would say the best way to do this is to just look at the validation. When you stop improving, that's when you should stop training your model, because if you train further, you are overfitting. Yeah. But your first question is asking if there like I interpret it this way, I'm not sure if it's correct. So if there are like an intrinsic limit that your neural network cannot do better. Yes. Like it can be some kind of hardware limit, right? For example, your detector resolution is just at this point, so you cannot improve any further. This is totally possible. So there are, we are like, your detector is not perfect. It cannot distinguish the thing it cannot distinguish. It doesn't have enough information to. So is there a way to know what that value is? I guess my answer is no, which is kind of similar to the previous question I answered about is there a way to find the global minimum? And I think the answer is no. So I think the best we can do is to perform the evaluation and get it to a point that we are satisfied. So for example, if you are building a signal versus background classification model, like we are actually doing this in Marana. So we are building a machine learning model to classify this single-side versus multi-side events. And we reach a performance, but the performance is actually very similar to our traditional method. So, we have been trying very hard, but it's very difficult to improve further on that. So that probably means we are reaching the intrinsic limit of the resolution of your detector, right? You cannot improve further because your detector is just providing you this amount of information. So
But there is no like, for example, equation you can plug in to calculate what that limit is. So it really just depends on what you actually get from training the model. So machine learning is, that's why people are calling it like experimental science, because you're just trying things out until a point that you are happy about. And I think this is also what we should do here, basically. Yeah. Good. Yeah.
Yeah, so my question is actually slightly related to the previous one.
Okay.
So is that possible that training actually making the model worse instead of making it better? And how we gonna do from that?
Well, the case of training actually making the model worse is basically overfitting, right? So your loss on the training data set keep decreasing, but when you are generalizing, when you are applying it to the out of sample events, the event that you are not training over, is actually giving you a worse performance. Actually, let me follow up on that a little bit. So when your machine learning model, let's say your machine learning model reach this point of accuracy and is no longer increasing, there are two possibilities, right? One possibility is you have exhausted everything, every single piece of information in your data, and it cannot improve further unless you upgrade your detector, unless you get the $2 million to upgrade your detector. So the other possibility is your neural network is not powerful enough to capture every information in your detector. So we'll actually talk about that tomorrow. We will see some cases where if you build a more powerful neural network, you can do a better job with the same detector data. But there is no kind of equation that you can plug in to understand exactly what's the maximum amount of information we can extract from our detector. Yeah, if someone can come up with that equation, that's going to be very useful, I think. Yeah. Okay.
So I think maybe in the interest of time, we're sort of hitting some of the questions that are going to come up tomorrow.
Okay.
People are welcome to keep coming down and ask questions.
Sounds good. Yeah.
I'll let you rest your brains.
Sounds good. That is